Hi, everyone, and welcome to the first of 5 in our Thermal Management Virtual Academy. My name is Nick Capelli, and I'll be taking you through TM 101 Why Thermal Management. So, today we'll cover a number of different things. First, we'll be speaking on the 4 W's of thermal management: what it is, why do we need it, who needs thermal management, and when would you want to use it in your application. We'll also be discussing the different types of thermal management along the way, and I'll give you a hint: there's a lot. We'll also be discussing some common applications where thermal management is crucial, and finally, what to consider when selecting the right thermal management for your design. As a reminder, we will be live tweeting today, so please follow us at Lord Corporation and feel free to use the hashtag thermalmanagement101 to join in on the conversation. Speaking on Parker Hannifin, looking at us at a glance, we have 3,000 different product lines in 50 different countries, but we are a global business with a local focus, which you can see is evidenced by our 290 manufacturing plants worldwide. So speaking on Parker Lord, this is a company formerly known as Lord Corporation that was acquired by Parker Hannifin at the end of 2019. And at Parker Lord, we're known for being a very collaborative partner, working to deliver solutions to meet your specific needs, as well as having a great network of global support. Speaking on our global support, you can see a map of all of the Parker Lord manufacturing locations around the globe. Most of the materials that we'll be speaking on within the next 5 presentations are made in the United States, in both Indianapolis and Sagertown, in Huckelhofen, Germany, or in Shanghai in China. Speaking on our expertise, we have a number of different markets where these thermal management products are used. Most notably, of course, is the automotive market, especially in the electric vehicle industry, as that's the booming trend right now in electrification. Many of our key products include thermal management and electronic materials, adhesives and coatings, sensing systems, electromechanical and motion and vibration control systems, and finally, motion and vibration control assemblies. But as I mentioned earlier, we will be focusing mostly on thermal management and electronic materials. So let's start out with our introduction to thermal management. So starting with the basics, what is thermal management? Well, to simply define it, and this picture does a really nice job, it is just taking hot and moving it to cold. The idea here is to remove the heat from certain components and transfer it away so that your whole system is operating at a lower temperature. In the context of electronics, this means that you're taking heat from components and then putting them into a heat sink. As far as what is a component, well, this differs upon each application, but components may include batteries, semiconductors, inductors, transformers, capacitors, etc. There are 2 main types of thermal management that we'll be talking about today. The first are passively cooled systems, and then the second are actively cooled systems, and we'll go into more detail on those later. Why is thermal management important for electronics? Ultimately, it comes down to 3 categories: performance, lifespan and reliability, and charging. Speaking on performance first, everyone is interested in products that are faster, but also occupy a smaller space. Therefore, they're more power dense. The problem with this, though, is that as you make something more power dense and there's less space involved, but still the same amount of power, it means that you produce more heat in this small space. And if you produce too much heat, the components will get too hot and then they'll malfunction. So as a result, there's a greater need for thermal management. So to use thermal management is extremely important so you can force more heat rejection out of this smaller space to allow the components to still produce at their optimal levels. Speaking on lifespan and reliability, exposure to heat will shorten the lifespan of the electronics and therefore their likelihood of functioning correctly. This is kind of similar to if you were to keep milk on a scalding hot porch versus keeping milk in your refrigerator. You're not going to want to drink the milk after it's been out there for any amount of time in the heat, but you're willing and able to drink the milk that's been in the refrigerator because it's been kept at a lower temperature and therefore it's still fresh and safe to drink. The same kind of applies for electronics, where if you're keeping them at temperatures that are cooler, in this case closer to room temperature, it extends the lifetime of those electronics. Something else to mention, though, is that not just speaking on temperature, but also about environmental protection, electronic materials and thermal management materials can double as environmental protection. So they'll be protecting these electronics from things like oils, greases, salts, acids, bases, anything that could negatively affect the lifespan or reliability of the components. Finally, thermal management is important for charging. Of course, all of these electronic components, such as lithium-ion batteries, will heat up during charging since energy is being added. And because these components are only rated to certain temperatures, the temperatures must be controlled during the charging process so that these components don't overheat. Because if they overheat, once again, they malfunction, and that just kills the ability of this product to function. The problem with charging, though, is that most of us are hoping that charging will be kind of like filling your gas tank, whereas it's done in a matter of minutes. But if you limit your energy input for charging, your heat may be lower, but then your charging will take too long. Therefore, for us to try to get charging down to the speed of filling your gas tank, the energy input needs to be high into your vehicle. But to counteract this, heat removal also needs to be high. So that's why thermal management is extremely important. So you can have that high energy input while still having a high amount of heat removal, allowing for faster charging. So what needs thermal management? And I think these two pictures do a really good job of describing this. You can see a small component on a printed circuit board all the way up to a big airplane, right? It's going to be for components small and large, applications small and large, and anywhere in between. And like we've mentioned before, we see this in a lot of different markets. Automotive, of course, being the most common, but also transportation, trains, planes, and automobiles. Those are the big things. Lighting, laptops and smartphones, energy storage, and finally microelectronics, like the individual circuit board component you see here on our left. So when should you think about thermal management? This is something we're asked very often in our roles, and the answer is always as soon as possible. Whenever you're designing something, introducing thermal management from the start allows the solutions that we have for thermal management to develop with the design. Whereas if you're trying to incorporate thermal management after the design has been finalized, sometimes you're limiting yourself on how you're able to implement these solutions and therefore limiting yourself on the ability to remove heat. So once again, it's really, really important that thermal management is thought about as soon as possible. So let's talk about thermal management solutions. We'll start first with potting and encapsulation. Potting materials or encapsulation materials are low viscosity, self-leveling materials. And viscosity, just to define this, is the resistance to flow. So something that is low viscosity has a low resistance to flow. Therefore, it flows very easily. These potting and encapsulation materials are designed to fill small spaces around electronic components to provide heat transfer, electrical insulation, and environmental protection. And as you can see in the picture on the right, I think this does a really nice job of illustrating the 4 different purposes that these materials might serve. First on the top left is potting. And this is where you have a housing or some casing, and there's a component inside, and the material is poured inside this housing and fills around the component to completely surround it. Encapsulation, as you can see on the top right, is where a mold is used and then the material is poured inside that mold and around the component. But then after the material has cured, the mold is removed. So now that material is the outer housing instead of, as in the other pictures, you can see there's that blue housing that remains intact. In encapsulation, the blue mold is removed, again, leaving the material as the outer housing for the application. Looking in the bottom left, we see sealing. Sealing in this case is going to be where just you're covering one specific end or side of the component with this material and allowing it to cure. Once again, still staying inside the housing. And finally, with casting in the bottom right, the idea here is that you're using a material to mold it into a specific shape or pattern within a housing. Then that molded material will be placed in contact with some sort of component that then needs the thermal management, the environmental protection, or whatever it may be. So these materials may be cured at either room temperature or with heat, and they can be easily applied by pouring them, using cartridges or syringes, or using automated dispensing equipment. Next, we have structural adhesives. Structural adhesives are typically thixotropic materials that are used to bond substrates together to replace mechanical fasteners or welding. Thixotropic, to define this, is a material with viscosity that lowers over time with increasing shear. This can also be referred to as non-sag or non-slump. In general, structural adhesives are dispensed as a bead, kind of like toothpaste on a toothbrush, right? It's dispensed and it stays in place, it doesn't move after that. These can be used to bond many similar and dissimilar substrates, but most commonly they're used with metals and thermoplastics. Structural adhesives are often used in lightweighting parts or components. They may or may not be thermally conductive, but the thermally conductive structural adhesives do combine the benefit of excellent heat transfer as well as a high bond strength. These can be two-component or one-component materials, and that always depends upon what is needed for the application. Two-component materials, or 2K materials, are typically used for larger parts and are room temperature cured, whereas 1K or one-component materials are typically used for printed circuit board applications and are heat or moisture cured. And all of these structural adhesives can be easily applied using cartridges or with automated dispensing equipment. Now, as you can see in the top of this picture, there are three different ways to bond two substrates together. And each y-axis of these pictures shows a force required in bonding. So as you can see in the leftmost picture with the rivets or the screws, there are individual stress points where each rivet or screw is. So the force on the substrate is maximized around those rivets or screws. Moving to welding, you can see that the overall force is slightly lower, but it's still not completely even across the whole welding line. And finally, moving to adhesives or the bonding picture in the top right, you can see that the ultimate force is lowest amongst the entire bond line, and it's completely even throughout, which is a benefit to adhesives over these other two types of fastening because it provides less force and it's going to be more even force, ultimately leading to better lifetime and reliability of this component. Now moving to gap fillers, these are an interesting hybrid between potting materials and adhesives. They have the rheological properties of adhesives, typically, but then the mechanical, electrical, and thermal properties of potting materials. Speaking on the word rheological, this just means related to the flow of the material. So a gap filler, for example, is dispensed in a bead, kind of like toothpaste, non-sag, non-slump, won't move anywhere once there's no more shear applied to the material. Now, gap fillers are liquid dispensed, and they do cure in place, and they're used primarily as a thermal interface material in large-scale applications between hot components and a heat sink, but where you don't necessarily need any great adhesion. It's really more to be used as a thermal interface material than a structural adhesive. Also, because a lot of these materials are used on things like battery cells or battery modules, they are designed to be serviceable. No one wants to have to throw away an entire battery pack if just one cell or one module goes bad. So instead, if you can take a gap filler, scrape it away, and then dispense new gap filler followed by a new battery cell or a new battery module, you're saving yourself and your consumer a lot of cost. Often gap fillers and their ultimate purpose was designed to replace thermal pads in large-scale applications. Thermal pads require a constant pressure to be applied in application, which means that you're putting a lot more stress on the components, whereas gap fillers, because they're dispensed as a liquid but cure in place, they're able to fill all the small nooks and crannies in each application, but then don't require constant pressure over the lifetime because the liquid nature allows them to flow into everywhere they need to be. These gap fillers may be room temperature or heat cured, and this is all depending upon what the person using them needs, whether they need it faster or they can work with a slower cure. And then finally, they can be applied using cartridges or automated dispensing equipment. Moving next to greases, gels, and underfills, we'll start with greases and gels. I like to look at greases and gels as something similar to a gap filler, but these are typically only 1K materials, and they're used instead of for larger scale applications, typically just for individual components on a PCB. These may be electrically insulating or electrically non-conductive. Greases don't require cures, whereas gels do. One of the benefits that these have over some things like gap fillers, though, is that greases and gels, because of the filler particle size in each type of product, they allow for very, very thin bond lines. And the thinner the bond line, that means the faster the heat transfer. So this is a big selling point for individual component thermal management because you want to transfer the heat out of those individual components as quickly as possible. These are also serviceable or reworkable. Again, so if you have a component go bad or if you have something slip off, you're able to service the material, scrape it away, dispense new material, and then reapply whatever you need to so that you can still use the component without having to change out the entire PCB. Because these materials are typically 1K, they're usually not applied in cartridges, but rather in syringes, and also can be coupled with automated dispensing equipment. Now, speaking on underfills, underfills are kind of like the potting materials that we talked about earlier, but these are usually limited to just one chemistry, and that's the epoxy chemistry. And these are typically only one component materials. But instead of encapsulating over something, these are actually filling underneath, yet still providing some of the same benefits like thermal conductivity, like electrical insulation, and underfills as a result of being used and filling underneath the component. They provide some structural support for these components to remain on the PCB. These also, like the gels and greases, can be easily dispensed through syringes or may be coupled with automated dispensing equipment for higher volume application. Now moving to coatings, coatings are going to be typically used in one major way in electrification, and that's going to be as a dielectric barrier in high voltage applications. Now, some of these coatings may be thermally conductive, some of them may not be, but anything thermally conductive will have the added benefit of allowing heat transfer to be faster. And of course, everyone is looking for more power density, so faster heat transfer is going to ultimately be better for these applications. Typically, coatings are applied somewhere around 75 to 100 microns thick. And then they also, in addition to providing dielectric strength and heat transfer, will provide environmental protection and corrosion resistance. Most of these coatings are going to be spray applied either manually or using automated equipment. However, some of them can also be dip or flow applied. And looking at some additional thermal management methods, we're going to be talking about 5 different types here. So thermal pads, which I've mentioned a little bit about already in our gap filler section, a thermal pad is essentially a pad that has an adhesive back to it. So instead of being a liquid, it's already in a solid, and all you have to do is peel off the back and then stick it on the component kind of like a sticker. And then from there, you mate that thermal pad with the heat sink, and then the heat can be transferred out of the components and into the heat sink. These do come in typically large rectangles or squares, though if you need them to be cut to a certain shape, you can use a die cutter to cut them to a certain shape, or maybe you're lucky enough in that they already come in the shape that you need them to be in. Looking at thermal films, laminations, and tapes, the idea here is similar with thermal pads, is that there's an adhesive back, and this is just a very thin film that can be stuck on some hot component, which then allows heat transfer from the hot component to the heat sink. Looking next at phase change materials, these are materials that start at a solid at room temperature, but then as the temperature increases, they melt and they become a liquid. And then that liquid allows the bond line to be thinner, which then will allow for faster heat transfer, like I mentioned before with the coatings. And then finally, we'll talk about fluid and air cooling. So these typically are more active systems. Fluid cooling here, you're forcing usually some sort of water, glycol, or oil through channels within a heat sink or heat exchanger to allow this cold fluid to essentially pick up the heat that's being generated by these components and then forcing it out and away from those components so you can keep them at a lower temperature. And then air cooling is going to be similar, but you're going to be using either active, so forcibly convected air with something like a fan to push the heat out of an application, or if the application calls for it, possibly just the natural convection of the air allows for heat to be removed from the system. So talking about 4 major chemistries here in thermal management, we have silicones, epoxies, urethanes, and acrylics. I do want to mention ahead of time that we will be discussing these 4 chemistries in our other thermal management courses, numbers 3 through 5. So please do tune in for more details on those. But for now, we can talk a little bit about each one. Starting with silicones, silicones operate at a very wide temperature range and are flexible, which allows them to protect fragile electronic components. They also may be filled or unfilled to provide different levels of thermal conductivity and have different curing mechanisms, whether that's addition cured or condensation cured. Addition cured materials typically are the higher performers, allowing for UL RTI ratings of 150 standard, and then also many of these can achieve a UL 94V0 rating for flammability. Moving on to epoxies. Epoxies are typically rigid systems that are very excellent adhesives, though some can be flexible. They also provide very, very good chemical and environmental resistance, as well as good high temperature tolerance. These are also available in filled or unfilled versions, which then can yield different amounts of thermal conductivity, and then also help the different amounts of electrical conductivity, as well as the ability for these materials to be flame retardant. Moving to urethanes, urethanes are generally very low viscosity materials that are great for applications with cold to moderately hot operating temperatures. Typically, these materials will cure to anywhere from a soft gel to a semi-rigid material that can still provide protection to stress-sensitive electronic devices because they do still retain some flexibility even in their semi-rigid state. Also, generally, urethanes, when cured, are a very good moisture barrier. And finally, acrylics. Acrylics are typically used to bond metals, composites, or thermoplastics with little or no surface preparation or primers. These generally cure very quickly at room temperature, and they are tough, so that means they're very impact resistant, which is a really nice benefit in applications where crash durability is important. Finally, these acrylics generally have very good low and high temperature performance. Now let's move on to the applications for thermal management and where it's used. So some common applications we have, as I mentioned already, transportation, right? That's going to be the big one. Planes, trains, and automobiles, the main ones. And of course, marine, construction equipment, things like that. So you'll see battery packs, motors, chargers, infotainment systems, chip level electronics, headlamps, heat spreaders, all part of the transportation applications. Looking at something like consumer electronics, you may see thermal management needs in antenna modules, CPUs, and sensors. Energy storage, once again, we have batteries, capacitors, converters, and inverters. And in robotics, we can see LEDs, microprocessors, motors, semiconductors, and sensors. So how do you choose the right thermal management material? There are a number of different things you should consider whenever looking for the right thermal management. First is performance. So often as an application engineer, we'll go through different questions with customers and ask, what exactly do you need for this material? Things to consider are thermal conductivity, dielectric strength, product lifetime, environmental concerns, vibration and shock profile, mechanical strength, reworkability, and flammability. Every application is different, so it's really important that you try to answer all of these questions ahead of time so you can help yourself as well as anyone else assisting you in determining the right material for your required performance. Chemistry. As we mentioned in the earlier slides, the silicones, epoxies, urethanes, and acrylics all have very different properties that can lend well to certain applications but not well to others, depending upon what performance requirements you have. So choosing the right chemistry is going to heavily assist you in having the right performance. Next, you want to consider assembly. So this is going to be really in the manufacturing setting. What sort of pot life or working time do you need? What sort of gel time do you need? Gel time is going to be the time where it won't blow anymore. The time to handling strength. How much time can you wait until the material can be removed from the fixtures or until the application can be moved from one step to the next? And then finally, cure time. At what point do you need the full properties of this material for either testing or for actual use in its lifetime? And then finally, application and dispensing methods. Every material has many different ways that it can be applied, but it's also really important that you choose the one that's going to fit best with your needs. So viscosity is going to be a major factor in this. Do you want something that flows easily? Do you want something that is thick and doesn't move? Uh, and how do you want the material to flow? Do you need it to flow from bottom up, from top down? Things to consider. Thixotropy, we talked about this before too. Do you need something that once it's dispensed, it will never move and it can be vertical against a 90-degree surface, or does it need to be able to flow freely? And then finally, filler type and degree of abrasiveness. This is something that's been really popular as thermal management has become more popular because filler is required to add thermal conductivity. But as a result, you're adding these solid particles that can be damaging to the equipment. So you have to make sure that the equipment is designed properly for the right material that you're using. So to summarize today, here are the key takeaways. The first is that thermal management is the removal of heat from something so that it doesn't malfunction. Thermal management allows components to have better performance and longer lifespans, also faster charging. It can be required for applications both large and small. It should be considered as soon as possible so that it can be developed with your component design. There are a lot of thermal management solutions available on the market, like we discussed previously and as seen below. And finally, choosing the right solution is the key to a successful design. And now finally, we'll start with questions. But before we do that, I want to remind everyone not to forget to register for our next upcoming Virtual Academy sessions. The next one will be Thursday, February 11th, titled Understanding Technical Terms. You can use the QR code in the top right corner here to register. Thank you for joining us.